discussing the properties of quantum material. So we are discussing the correlation, strong electronic property of the quantum material. So these property offer more sophisticated and approaches to the model and understanding the behavior of the strongly correlated quantum system by considering the dynamic nature of the electron correlation and the interaction. So techniques like DMFT focus on the local behavior of the electron, that providing insight into the effect of the strong correlation and the electronic properties. So this particularly useful for the one-dimensional system, offering the powerful numerical method to study the quantum many-body system. So the tensor network methods provide a framework to represent the quantum state efficiently, enabling the system of entanglement and correlation in the strongly correlated system. Another property is the topology and the symmetry in the quantum material. So topology and the symmetry is important in the quantum material. So the topology and the band inversion in the insulators defined in the figure. Atomic limit energy levels determine the natural order of occupied and unoccupied orbitals. Occupied defined by the blue and unoccupied defined by the yellow line. As the lattice parameters lowers, as the lattice parameter is lower, the gap between the occupied and the unoccupied block state close at a critical point and reopens inverted concerning and atomic order, achieving a topological state. So semi-metal topological state classification, material can be bulk band inverted to create the topological semi-metals. So crystalline, rotational or the mirrored symmetry protects the inverted valence and conduction band crossing left. So Dirac semi-metals have four-fold degenerate crossing points shielded by rotational symmetry in the presence of the inversion and the time reversal symmetries. So semi-metals have two-fold degenerate band crossings that forms a chiral fermions separated in a quantum space. So distance between the oppositely charged while nodals protects the faces. So there is defined the fermions and non-simorphic semi-metals generate the topological semi-metals without the bulk band inversion. So non-simorphic crystal symmetries protect the spin orbit coupling band crossing. So there is degeneracy and the energy momentum relationship near the band touching point classify the topological semi-metals. So you can see here that is the topological band inversion, that one define the topological and band inversion in the insulator. That is defined a critical point where these are touching, and lastly we are having a two bands here. So A is equal to infinite. So another is the semi-metal topological state classification, that is a topological band inversion in the insulator, but here in the semi-metal topological state classification, that is the graph between the energy and the crystal movement. You can see here the that there is a band inversion on the left hand side, you can see here, and on the right hand side there is a symmetry referred. You can see there is a symmetry, there is displacement in the symmetry from minus pi to the plus pi. So condensed matter physics, if we talk about, focusing on the particle systems, motion patterns and the law, has engaged as a vital subdiscipline. So discovery of the inter-quantum Hall effect, where we have an integer quantum Hall effect, that is IQHE, alongside subsequent finding of the various topological quantum state, that has unlocked a realm for the global scientists. So, topology and the symmetry play a crucial role in the quantum material by influencing their properties and their behavior. So, in realm of the quantum material, topology refers to the study of the properties that remain unchanged under the continuous deformations, like stretching or bending without tearing or gluing. Means that topologically it will not change whenever we just have the various deformation, still they just give the same properties. So, topology refers to the study of the properties that remains unchanged under the continuous deformation like stretching or bending. On the other hand, symmetry involves the operation that leave a system invariant. So, such as spatial isotropy, transitions, time reversal and the various internal quantum numbers is used in the symmetric. So, topology where we can just have the properties like which will be unchanged after the continuous deformation, but in the symmetry we have just having the operation that will provide the symmetry invariant such as the spatial isotropy, transitions, time reversal, various internal quantum properties. So, topology and the symmetry are fundamental concepts in the quantum material, influencing their phase, their property, their behavior by defining the symmetries, order parameters and the structural characteristics that underpin their unique quantum phenomena or their unique quantum behavior. So, topology is a mathematical idea that ignores the small details and gradual changes. So, now we can have the various applications where we can have the shape in the space, and this applies to the materials too, like how atoms are arranged in a crystal and how electrons behave in that crystal. So, these spatial materials called the topological quantum material and have the unique quantities because of their topological structure. So, discovery of the integer and the fractional quantum Hall effect, that is IQHE and FQHE, have unveiled a unique form of matter that is known as the topological quantum states. Investigating the topological characteristics of these materials involves identifying the similar properties in the electronic band structures and the physical quantities, leading to the physical state less affected by material defects. So, topology of the state refers to how electron states are organized in the material, that understood through unique numbers called the topological invariants. So, these numbers describe the shape of the electron wave functions in the momentum space. So, there are the unique numbers, that is the topological invariants that define the wave functions in the momentum space. So, a material with a non-trivial topological number has a unique electron wave function shapes and having a spatial surface or the edge state that can resilient to small changes in the material. So, an analogy is a unchanging basic shape of the object under the gentle deformation. So, in the topology, the appearance of these particular states in the material indicates a unique shape in its electronic wave functions that has been seen in the quantum Hall state. So, where the bulk becomes the electrically insulating under a strong magnetic field in the two-dimensional material. In contrast, the chiral conducting states form along its edges. So, these edge states persist despite attempts to eliminate them. So, making the Quantum Hall system, a precise standard for resistance and determining the fundamental constant like the fine structure constant. So, topology serve as a key way to organize and understand the quantum state. So, it is all about the shape of the electronic wave functions and how it behaves in the K space, which is a mathematical representation of the quantum state. So, the specific shape depends upon the symmetry of the group of the crystal lattice, similarly as in the topological state. So, these topological characterizations control how material responds to environmental changes and stay consistent even when the material's properties changed smoothly. So, imagine a scenario where the order of the electron energy level switches at a specific point near the Fermi level. So, this change in the order is like a band inversion, as we have seen. So, leading to a topologically in-trivial state. So, we can having the non-trivial state where the system is a in a non-trivial state. The change in the order is like to the band inversion, that makes it is a non-trivial state. So, we can say topology in the non-trivial state. So, these main methods are commonly used to determine the unique properties of the material. Number 1 is the directly calculating the specific characteristics that indicate their topological nature and the symmetry indicators. Second, employing a gradual transition to link the topological state of an unfamiliar material with that of a known one. Third is utilizing the relationship between the bulk and the surface state to identify the non-trivial properties of the material. So, first two involves analyzing the symmetry properties of the bulk state, often representing in their irreducible forms at the specific point in the Brownian zones, initially convinced as a parity creation for the materials with inversion symmetry. So, this method can expand to cover all type of the space group. So, third method, having unique state of the material by examining their connections with the bulk bands, offering the experimental clues to confirm their distinctive properties. Now, what are the application of the quantum material? As quantum material nowadays are used in the quantum technology and quantum computing, but apart from this forefront of the material science have ignited a revolution in the technology and application. So, these remarkable material with their unique electronic and optical properties arising from the quantum mechanical effect holds the immense promise for a wide range of exceptional applications, from ultra efficient photo detector to quantum computing. So, quantum material drive innovation and redefine the boundaries of what is possible in the electronic, energy storage and beyond that. So, we use this quantum material in advanced electronics. So, one of the application is the advanced electronics. Quantum material based electronic devices are technologically efficient and material sciences offering the remarkable properties and diverse application. So, quantum dot leverage quantum confinement effects for precise control over the electronic and optical properties. So, nanowires provide a platform for nanowire provides a platform for ultra compact high performance devices with exceptional electronic transport properties and versatile integration possibility. Apart from this, two-dimensional material like graphene and transition material dicharconides, that is TMD, enable development of the ultra thin or flexible devices with outstanding electrical, thermal and mechanical characteristics. So these quantum based material electron devices hold promise across the various fields including electronic, photonic, energy harvesting, quantum computing, fueling innovation and pushing technology boundaries. They represent the next generation of the transistors, sensors and high performance computing. As we are just talking about the Grover algorithm, Shor algorithm, so when we are talking about the high level computing, so we require the high level of the quantum material. So that must be superior performance as compared to the traditional electronic devices. So, so quantum, another application is the quantum sensing and imaging. So quantum material are used in the sensor technology and imaging. So they offer the unique properties like superconductivities and magnetism that enabling the ultra precise sensors for medical imaging and the environmental properties. So integrating quantum materials into the techniques like magnetic resonance imaging and the microscopic enhance the ability of the atomic and molecular structure exploration. So application include highly sensitive magnetometer for medical diagnosis and the quantum dot sensors for biomolecular sensing. So interferometry that also involve the quantum material such as Bose-Einstein condensates, and the atom interferometer offers the unparalleled precise in measuring the gravity and the other parameters. So the sensor that can detect minute changes in the acceleration and the rotation, that can find the application in the navigation and just sensing the other gases at the various level. In this section we can have the various application, but we will discuss some like the quantum drives a new sensor development and imaging era that is used in the various field, like in electronics, like in the mechanical, like in the vehicles, the various quantum sensing instruments. So quantum next application is in the quantum communication and the information processing. So quantum material plays several key role in the quantum communication and information processing. Like they just provide the efficient quantum memory system that store and retrieve the light generated quantum information. So deuterium based material for instance show the promise in this regard, and they store the protect quantum information at the high frequencies. So quantum materials are essential for realizing the quantum interconnects, including the components like quantum switches, repeaters and the frequency converters. So by using the quantum material we can prepare these type of materials, these type of devices. So these interconnects facilitate the transfer of the quantum states between the different devices while preserving the coherence and entanglement. Certain quantum materials serve as a platform for the implementing the qubits in a semiconductor quantum dot. Color centers in the wide band gap materials and the superconducting materials that enabling the diverse qubit type for the quantum computing. Actually, quantum material with the unique properties like diamonds with color centers are used in the sensing. Highly sensitive sensors are the various application of the quantum material. So quantum material have the used in the quantum communication security and enabling protocols like quantum cryptography and the quantum key distribution, which utilize the superposition and entanglement to ensure unbreakable data encryption and data transfer. Another application is the energy conversion and the storage. So in a quantum mechanical system, quantum material have emerged as the revolutionary component in energy conversion and strong devices, like transcending the limitations of the classical material. These is exceptional properties at the nanoscale that enable leap in the efficiency and the performance. So, in the energy conversion, quantum material use the various material that is in the solar cell that exhibits that will increase the fill factor and that can give the more efficiency in the solar cell system, and harvesting capabilities efficiently converting the sunlight into the electricity. Similarly, quantum dot offer the tunable electronic and the optical properties that enhance the efficiency of the LED and the photo detector. So, quantum material such as graphene and we can say carbon nanotubes in the energy storage contribute to superconductors and the batteries with enhanced charge storage and the faster energy release. Charge discharge must be in an efficient manner or in the faster manner in the quantum. So, quantum phenomena like entanglement can be leveraged to develop the quantum enhanced devices for even more efficient energy conversion and the storage, paving the way for sustainable energy future. So, utilization of the quantum material in the energy conversion and the storage devices in the quantum dot, solar cell, thermoelectric materials and the quantum enhanced energy storage. Another application is the spintronic application and the topological superconductors. So, topological superconductors, there are a various material that can be used conductive surface state protected from scattering by symmetrical constraint and non-trivial band topology. So, this property arises from the interplay of the quantum mechanics and topology, holds immense potential for quantum computing and spintronic. So, it just provide the stable qubits, less prone decoherence, crucial for scalable quantum computers, where in the spintronic they combine electron spin with the motion to create the efficient spin current that will make it a noble device functionality, and that efficient energy storage system can also store the data in a very good manner. So, topological superconductors with the surface metal and the interior superconducting state, they use the fermions for faultless quantum computing, while topological magnet exhibit a chiral edge state, merging magnetism and the topology for the low energy loss electronic devices. So, these quantum materials robust electronic state critical for reliable and the fault tolerant devices, and they are used for the various growth for the and the efficient use of the devices. So, device fabrication can be done by using the quantum material. So, quantum material for the quantum computing, as we are talking about the fast computer, so we require the efficient material. So, the exploration of the quantum material is used for the advanced quantum computing platform that leveraging the principle like quantum coherence, superconductivity and the topological properties. So, these pledged materials provide the physical platform for the quantum bits in the quantum computing. So, fundamental unit of the quantum information that allow the researcher to manipulate or control the quantum state. That is only possible when we choose the suitable quantum material for this. So, quantum material enables the development of stable and reliable qubits, which are essential for the complex calculation currently intractable for the classical computer. So, by focusing on the synthesis, characterization and utilization of the quantum material, the main aim is to unlock the full potential of quantum computing, quantum computation, moreover for the sensing purposes, for the we can say that for the various superconducting properties, for the so energy storage supercapacitors, so this quantum material profound implications across the diverse field of the science technology. So quantum material having creation of the multiple qubit system interconnected for the complex calculations, moreover leveraging quantum behavior like superposition and entanglement, superconducting material. For example, if we enable the creation of the superconducting qubits, which are crucial for operation of surpass classical computing capabilities. So, quantum error correction utilizing quantum material that creates the fault tolerant qubits that are less sensitive to environmental disturbances and which is essential for the reliable quantum computing. Quantum materials such as those as a superconducting qubits play critical role in specialized quantum computing approaches like quantum annealing and exploit quantum tunneling effect for the quantization problem. So, there is more to explore how quantum properties of the materials inspire novel algorithm for more efficient problem solving leveraging quantum parallelism and the interference. So, there are the another application also like metamaterials or the meta surface in the optics and the photonic application we use the quantum material. So, quantum material offers the vast potential across various applications, particularly in the computing, communication, energy generation and the material science. Thank you very much.